In Chapter 2, Section 2, we'll be talking about fractions. And I know how many of us absolutely love fractions. So let's go ahead and let's remember what they are. So a fraction represents a part over the whole. All right, that's really what a fraction is. So like, for example, the fraction 1/3, all right, could be written as, we have a rectangle where we have 3 pieces that make up this entire whole rectangle, except one of them is shaded. So this would be the fraction 1/3. Another way you can look at this would be if you drew like a pizza, but this is a little bit more difficult because you'd have to split it up into 3 equal pieces. But once again, you shade one of them and you get the fraction 1/3. On a number line, all right, it would be in between 0 and 1, and you would have to, once again, in fact, let me draw this a little bit more deliberately because you'll see what I'm doing. I'm going to draw this directly underneath of that shape, because you could see here that if I split this up into 3 regions, 1/3 would be this distance right here. All right, so there are 3 different ways that we just represented a fraction, which is a part over the whole. All right. So let's look at another example of representing a fraction like this. All right, we'll do 3/5 using the examples above. All right. Well, once again, if you want to start, I'm going to start with the circle first. This one's going to be a little bit more difficult, because like I said, you got to make sure they're nice and equal. And obviously mine are not perfect, and that's fine. But this is 1, 2, 3. So here's 3/5. Personally, I prefer the rectangle method. All right, where you would just shade in 3 out of the 5. So here's 1, 2, 3. And then finally, my favorite, which is the easiest once you understand the rectangle part, would be the number line. So right here would be 3/5. Okay, so notice here that even though I had 2 different fractions, I drew them using the techniques the same exact way. Not all fractions are created equally, all right? And that's because of the way that let me get out a better highlighter here. That is because of the way that fractions separate themselves into equal pieces, all right? So the big thing then is, well, what exactly are equivalent fractions? Okay, what are equivalent fractions? All right, so like, for example, we have 1/2 and 4/8. All right, are they equivalent? Now, all of us in the room, we've all seen fractions before. And we know 1/2 and 1/4 are equivalent. Like I'm positive that everybody in the room would get this correct. You would say yes, they are equivalent. However, you need to think about this in terms of somebody initially seeing this for the very first time. How would you demonstrate? How would you prove this to somebody? Right now, you and I are using our brains. We're using very abstract thinking. But how would you show this to somebody who's never really seen fractions before, and this is the first time? Well, why don't we just draw them and see what happens? All right? The fraction represents a part in the whole, right? So if we think about this rectangle in terms of a number line, we know this is going to be 0. That's going to be 1. So for 1/2, we're going to split this up into 2 equal pieces where we shade one of them. Okay? Now, if I do the same exact thing, same exact shape, all right, from 0 to 1, but this time I have to separate this into 8s, and I need 8 equal pieces. All right, and I'm going to shade 4 of them. 1, 2, 3, and 4. Notice that I've essentially shaded the same exact area. If I bring this down, I could like put it like right there. See, notice that I've shaded the same exact area. So visually, I know 1/2 and 4/8 are definitely equal to each other. All right. And that's what we mean by equivalent fractions. All right. And not all fractions are equivalent to each other. For example, we know 1/2 and 2/5. Well, are they equal to each other? Well, let's see. Let's do exactly what we just did. We're going to draw 1/2. All right. Then same exact area. Now we're going to do 1/5, or I'm sorry, 2/5. So here's 2/5. And notice that when I bring this down closer and closer and closer, they do not represent the same exact distance. In fact, you got all that, I guess, area, if you want to call it area, you got all that space missing. In fact, not only do we know 1/2 and 2/5 are not equal to each other, we also know, just by looking at this, that 1/2 is greater than 2/5 because the amount of area that I shaded for 1/2 is bigger than the amount of area I shaded for the 2/5. So we can even compare them using pictures. See, and this is how people, especially younger people, learn. If you ever watch a child playing, okay, what they're really doing is they're really learning. All right, they're using their hands, they're using manipulatives. All right, even though, like I said, they're playing, they're learning things. Here's a great example on how you can explain to somebody who's never seen fractions before not only the concept of equivalence, but you can also demonstrate the size of fractions. How are some bigger than others and stuff like that. So, I guess a picture is worth 1,000 words. In this case, absolutely. There's so much information here. But now, if we think about this in a more abstract way, in other words, now you're dealing with people who have seen fractions before, but now they, instead of drawing pictures all the time, because drawing pictures, it takes a lot of time and everything. How would you explain this to somebody who kind of has an idea of what's going on? All right, so like, for example, let's look at 3/4 and 12/16. All right, well, we could draw a picture here if we wanted to. And I'm going to tell you, yes, they are equivalent. I'm saying this right now. All right, yes, they are equivalent. All right. But a way that we can demonstrate this is, well, what if we started with the smaller one, 3/4, all right? Could we get the 12/16 by, I don't know, let's keep adding 3/4. So here's the first. So 3/4 and 3/4. Denominators are the same, so you can add them together. So that's going to be 6/8. I'll write it underneath. Let's add another 3/4. Well, if we add another 3/4, that's going to be 9/12. All right. If we add another 3/4, notice we get 12/16. So really what you did here, all right, is you took 3/4 and you added it 3 times. Think about that. You took 3/4 and you added it 3 times. So what we could say here is equivalent fractions can be created by taking a fraction, let's say 3/4, and multiplying it by n/n. In other words, the same exact thing. All right. So here we have 3/4, and let me kind of drag this out here a little bit. We have 3/4, and how many 3/4 do we have? In other words, how many total are we adding? Well, we're adding 4. So if I change this to 4/4, look what you get. 3 times 4, 12. 4 times 4, 16. So equivalent fractions are created by multiplying any fraction by n/n. All right. So example here, if I said create 3 equivalent fractions. Two 7s. All right. Well, the first one you could create would be, I don't know, let's say 2/2. So we get 4/14. There's one equivalent fraction. Here's another one. How about 7/7? Well, 2 times 7 is 14. 7 times 7 is 49. That's another equivalent fraction. And finally, the third one, we'll do 5. So 5/5. So that's going to be 10/35. But at the end of the day, here's what we know. 2/7 is equal to 4/14, which is equal to 14/49, which is also equal to 10/35. All right? So all these things are equal to each other. And we got that by understanding how to build equivalent fractions. The next thing I want to go over, all right, is my favorite concept. Simplest form. In other words, let's say we were doing a problem, and I know we've all been in this situation before. Let's say we came up with the answer x equals 10/35. All right. And you always heard your professor say, write your answer in lowest terms. Okay. And you were taught all these cool little tricks. All right. And the tricks that you were taught And I'm going to just pull out the internet right now. The tricks you were taught were called DIVISIVI, divisibility rules. And I know we all remember hearing divisibility rules, all right? And here are some of them right here, all right? Like divisible by 2, the last digit should be even. Divisible by 3, the sum of the digits should be divisible by 3. Divisibility by 4, and there's all these different rules, okay? But the problem with this is you got to remember all these rules. And how many of us have ever been in that situation where you had a fraction, let's say 10 over 35, and you started applying these rules, and you got to a point where you were like, I don't know if I'm even done yet, all right? So what I'd like to do is I want to show you, using what we just learned, equivalent fractions, I want to show you a simpler method that, like I said, not only is simpler, okay, but at the same time, it visually shows you when you were done, all right? So the method that we are going to use is called prime factorization, all right? You have no idea how unbelievably special this technique is. It's unbelievable, all right? So just to recap real quick. Prime numbers, 2, 3, 5, 7, 11, 13. They keep going, all right? So those are prime numbers, all right? Prime numbers, what makes them special, the only factors, meaning numbers being multiplied, all right? The only factors are 1 and the number. Oops. All right, so like, for example, the only way to get 5 is 1 times 5. The only way to get 13 is 1 times 13. Now, this word, factorization, I kind of already told you what that is. Factors are numbers being multiplied. The ization part of this is just saying, okay, write them out. So, for example, 10, its prime factorization is 2 times 5. 35, its prime factorization is 5 times 7. Now, I want you to look at what I did here. There is something that I did that is extremely important. Please note that the 5s in both prime factorizations are on top of each other. And the reason, and watch this, this is how easy this is. If I had the fraction 10 over 35 and I wanted to reduce it, all I have to do is write the prime factorizations and then look for the equivalent fraction. And the equivalent fraction is right here. And I know if I have an equivalent fraction, like 5 over 5, that reduces and turns into a 1. So really what we have is 2 times 1 over 1 times 7, or 2 over 7. Yes, every single fraction that you've ever seen can be broken down into prime factors, and then using equivalent fractions, what we just learned, you can quickly simplify them. All right? Let me show you another example here. I'm going to take it directly out of your book. Simplify 24 over 40. Well, let's do the prime factorization of 24. So two numbers that multiply to give me 24. How about 4 and 6? Now, since neither of those are prime, we're going to keep going. 2 and 2, 2 and 3. So this is called a factor tree. And all these like little lines right here that I'm highlighting, those are just the branches. That's it. That's it. But what I do know is this. I know 24 is 2 times 2 times 2 times 3. That's its prime factorization. Okay? Now I'm going to do 40. 40 is 4 and 10. 4 breaks down into 2 times 2. 10 breaks down into 2 times 5. So 40, 2 times 2 times 2 times 5. And watch. Please just watch the screen. I'm going to zoom in. Here we go. 24 over 40. All I got to do is find the equivalent fractions. Here's one. Here's another. Here's our third. Reduce, 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 and look what's left over. 3 over 5. So 24 over 40 reduces into 3 over 5. And notice, I did not use any divisibility rules, and I can physically see when I am done. How do I know? There are no more numbers that I can reduce. There are no more what we call equivalent fractions because we reduced them all. They all turned into a nice number 1. So I hope you learned something here. I hope you learned and you're like, oh my gosh, simplifying fractions, is that easy? Yes, it is. All right, it is this easy. It's just once you get really comfortable with this, maybe the divisibility rules get you from 24 over 40 to 3 over 5. Maybe it gets you there faster. But I got to be honest with you. I don't care how fast you get to the answer. I just want you to get to the answer. And I want you to get the correct answer. All right? So, excuse me. So I hope you learned how to go ahead and use this technique of prime factorization, all right, to simplify fractions. All right? Because like I said, it's very, very, very powerful what you can do with prime factorization. The last type of fraction I'd like to talk about are going to be mixed fractions, or mixed numbers, we call them. Okay? And this is extremely straightforward, especially given our approach to all these fractions today, which was, a lot of it was visual, okay? So like, for example, 1 and 1/2. Well, what does that actually look like? Well, once again, if we were to create a rectangle, and let's focus just on this. All right, the 1/2 part. Well, that denominator says you're going to separate this into 2 pieces. Here's our 1/2, right? Well, the front, which we call the whole number, would be represented like this. It would be another rectangle split in half, except you have both pieces shaded. That's what makes it one entire whole. So this would be the fraction 1 and 1/2. In fact, I think it probably makes more sense if I drew it like this. So here's our 1 and 1/2. And when you think about it, in order for us to get 1 and 1/2, you have to add these two things together. So even though we write 1 and 1/2, another way we can write this is 1 plus 1/2, okay? But normally, we don't even write the plus sign. We just write them right next to each other, just like that, okay? So how would you draw this on a number line? The same exact way. So 1 and 1/2. We know we were separating from 0 to 1 into 2 equal pieces, but it also means we're separating 1 to 2 in 2 separate pieces. In fact, infinitely going to the right, you would be separating them into 2 pieces because the denominator is 2. It tells you how many equal pieces to kind of subdivide this into. Now, going from left to right, and I'm just going to draw this so you can see it. Right here is 1/2. Actually, no, I'm going to do it above. Here is 1/2. Here is 2 over 2. Here is 1 1/2. And here is 1 and 2 over 2. But remember, I said you can add these things together. We know 2 over 2 is really plus 1. So this would just be 2. And that's how we get this. So 1 and 1/2 would be a dot right there. All right. So I hope this makes sense, because visually, it's so much more powerful than just always thinking about it. All right? So that's going to be it for this video. And if you have any questions, let me know. See ya.